Okay, we were talking about work integrals, and another method that can be used to compute or evaluate work integrals in certain situations is to use Green's theorem. And those situations are the vector field is two-dimensional, just x and y, no z, and the path of integration is closed. It comes back to itself, a closed loop or path. And in that case, this work integral, or this work integral, becomes a double integral. And we talked, the previous two videos were on was a review of double integrals. So it's just the partial derivative of q with respect to x minus the partial derivative of p with respect to y. That becomes your integrand over the region of integration, and that region is the region bounded by the path. And your answer will be positive, well, positive direction is counterclockwise around the region. Get a negative answer, it means, well, never mind. If your path is counterclockwise, this will give you a positive answer. If you wanted the path to go clockwise, it's just a negative of this. Shouldn't say it gives you a positive answer. This might turn out to be negative, but it means the work integral going in the counterclockwise direction. Let's do one. Here's the work integral around the closed circuit, the complete triangle with these vertices. So let's graph that triangle first thing. 0.12 is here, 2,2 is here, and 2,4 is here. And it says clockwise, so here's the path of integration. So the R, the region of integration, is this shaded region, this triangle here, triangular area. Let's see, here's the Q. Its partial with respect to x would be 3y squared. Here's the P. Its partial with respect to y would be 2x. So the integrand is 3y squared minus 2x. And let's see. I'll integrate over y first. Then y would go from 2 up to this line here, which goes through 1, 2, and 2, 4. So it has a slope of 2 and it goes through the origin. It's just 2x. Y goes from 2 up to 2x, and x goes from 1 to 2. Your boundary's right. That's part of the setup. After that, this is a normal integral. I'm not going to go through that. Hopefully you can take integrals, iterate, first do the inner integral, and you'll end up with this, and then do the outer integral. Here is the setup, including the limits. The limits are important. How about another one? Here's the work integral going completely around this circle, radius 2. So let's see, here's Q. It with respect to x will be 6x squared. And P with respect to y will be minus 6y squared. I subtract Q sub x minus P sub y, so it'll be 6x squared plus 6y squared. And what's the region of integration? It's just the circle of radius 2. So I'll do polar coordinates. I can pull out a 6, and x squared plus y squared is just r squared. The extra r, polar coordinates. I'll do it dr d theta, so r goes from 0 to 2 because the radius of the circle is 2, and pi goes all the way around because it's the whole circle. Here is the setup. This is the kind that splits up into a product. So it'll be 2 pi d theta, which is just going to be 2 pi, and then r cubed from 0 to 2. How about this guy? Here's work integral over the path is an ellipse. And let's defer this for now. Let's first just do our P's and Q's. Q with respect to X will be 2 e to the 2x times the rest of it. And P with respect to Y will be 2 cosine. Oh, they're the same thing. So when you subtract them, you get 0. So the answer is going to be 0. We don't even have to take it. And if you go back, Q sub X equals P sub Y in 2 dimensions means it's conservative. And if you go around a closed path in a conservative vector field, your answer is always going to be 0. Do one more. How many more we got? Two more examples. So here we go. Let's see. Bounded by x equals 0, so there's that line. This guy, a circle of radius 1, and x is greater than or equal to 0, so the path encloses that region. It's this semicircle. So the region of integration is this semicircle. Here's Q. With respect to x, it's going to be 2x. Here's P. With respect to y is x. So 2x minus x is just x. There it is. And dA, but you to do in polar coordinates. So x becomes r cosine theta. Extra r here. Really r squared cosine theta, dr d theta. And r will go from 0 to 1. Theta goes from minus pi over 2 to plus pi over 2. Get your limits correct. Again, this guy splits up as a product, r squared part and the cosine theta part. So let's take these two integrals normally. I'm not going to do that. There's the answer. One last one. This guy with respect to x, 0. P with respect to y is 2xy. I have two curves. These two curves, well, they form a path. The path that encloses the bound, the region. I think the wording of this problem. And be careful here. X cubed between 0 and 1, between x equals 0 and 1, is below x squared. So this lower one is y equals x cubed. The higher one is y equals x squared. Once you get past 1, the x cubed wins. So let's see. I already did the p's and q's. It's just 2xy. Did I do that? This guy with respect to x is 0. This guy with respect to y is 2xy. I don't polar coordinates, so let's see. The integrand is going to be 0 minus 2xy. And let's see, I'll do it over y first. And y will go from x cubed to x squared. On bottom, x squared on top, minus 2xy dy dx, and x just goes from 0 to 1. There is the setup. Iterate the integrals. I have a what? Xy squared, still a minus. Evaluate it between those two limits. This. Here we go. That's Green's theorem. And that covers almost the work integral. We're going to start surface integrals, and the work integral will crop up again when we get to Stokes' theorem. But surface integrals will be the next subject. That almost completes the work integral.